So in this video, we're going to do a review of trigonometry. And really all of trigonometry is based off of one simple thing, and that simple thing is the unit circle. So the unit circle is just that. It is a circle. Let's start there. It is a circle of radius 1, so this distance from the center out to here or out to anywhere is 1. And it is centered at the origin. So one thing people forget about a lot of times is that the unit circle is on our xy coordinate system. So here's our x-axis, here's our y-axis, and its line in our coordinate system has a radius of 1 and it's centered at the origin. That is the definition of the unit circle. Okay, now one thing that we're a lot of times interested in is kind of where these points are on the unit circle. And there are a few different ways that we can describe that. Of course, I could just pick a point and say, well, this is the coordinate point xy. But another way that we can take a look at where we're at on the circle is by thinking about what angle is spanned to get to that point. Now, there's a few different ways of measuring angles. Of course, one of them is degrees. That's the one that you're most familiar with, the one that you were taught right from the get-go. And if we think about it, well, if I were to start here and go all the way around the circle, we all know that that would be 360 degrees. So in the unit circle, we have 360 degrees. Now, have you ever wondered where that number comes from, the 360 degrees? Here's the thing, is that somebody just made that up at some point. Someone just said, hey, let's go ahead and make the circle have 360 degrees in it. Why not? And a lot of people think that that was based on the calendar, that there are 365 days in a year. And of course, though, 365 is not very divisible. However, 360 is a very divisible number. It's divisible by 12, 10, just lots and lots of different numbers. And so that's some of the reasons why this was chosen to be the amount of degrees in the unit circle, or in any circle, really. It doesn't have to be the unit circle. Okay, so we're going to move away from degrees. I don't like the fact that somebody just made that up at some point. Let's go ahead and talk about another way of measuring the span of this angle, and that is going to be what we call radians. Okay, so by definition, 1 radian is basically the angle that is spanned by the same length as the radius, I guess you could say. Let me explain that a little bit better. So if I take my circle and I start here, let's take a look at this distance right here. Okay, so the distance from the center out to this point. Now we know that that distance is 1 because again we're on the unit circle. So 1 radian, if I wanted to look at 1 radian, that would be how far up the curve I would have to go so that this distance is the same as this distance. So let me think about when I would need to stop here. So I'm trying to make this length the exact same as this length. That kind of looks like maybe I should stop right about there. So if I stop here, the angle that's spanned here is exactly 1 radian, if those two lengths are equivalent to one another, and that is 1 radian. Okay, so I like radians because of the fact that it actually describes a physical attribute of the unit circle. So if we think about then how many radians there are in the entire unit circle, that is, if I start here and go all the way around, how many radians would that be? Well, that would be the arc length from here all the way around. So essentially, if you thought of yourself as maybe standing on a circular track, and we started here, the distance it would take to walk all the way around in a circle. And hopefully you can see that really what I'm describing is the circumference of the circle, right? Just the circumference. And we know from the equation 2 pi r that is the equation that we can use to find the circumference of a circle. And in this case, my radius is 1, again, because it's the unit circle. So the circumference is 2 pi. So that is the number of radians in the entire unit circle. And for that reason, we can actually even say that 360 degrees is the same thing as 2 pi radians. And if we wanted to, we could do conversions from degrees to radians. I'm not going to worry about that too much, because really we're going to stick with radians in calculus. Okay, so this is our basis. Basically, to go all the way around the circle, we go 2 pi radians. Now, there are certain angles on here that we're really interested in, kind of just nice angles that split up the circle into an equal number of parts. Okay, and so one of those is, of course, a 30-degree angle. I can take 30 degrees, 30 degrees, 30 degrees, and that basically splits this part up into 3 pieces. And I could do that for all of this. Okay, so, and another one that we're interested in is, and I kind of almost drew it here, is our 45-degree angle also. So what I'd like to do is, let's take a look at the unit circle. Okay, so here it is. All right, so here's our general unit circle, and what I've done is I've split it up into 2 different components, essentially. One of them is the breaking up into 30-degree angles, and the other one, the orange one, is the breaking up into 45-degree angles. Okay, so let's take a look at those 2 pieces separately for right now, and then we'll kind of think of them together. So here's one thing I'd like us to go ahead and think about, is if there are 2 pi radians in the entire unit circle, how many radians should there be in, let's say, maybe just this first piece? So this angle, essentially I'm asking the question, what is this distance right here? Now notice that with the yellow part, the yellow one, we have split that up into, well, let's see, just this first wedge is split into 3 pieces, if we just look at the yellow one. So that means then we've split the entire unit circle into 12 pieces. If we look at the orange one, we split each quarter of the circle into halves, so that would give me a total of 8 pieces. So what we're going to do is we're going to think about what each of those pieces is worth as far as angle-wise. So going all the way around is worth 2 pi radians. And I notice I have 12 of these yellow wedges. Okay, so that means that each one of them is 2 pi over 12 radians. And of course that simplifies to pi over 6 radians. So that means then that this first angle that I have here is a span of pi over 6. So I'm going to write that part in there. I'm going to use these little lines as my fraction mark. So pi over 6, that is the first angle there. And now, because all of these wedges are equivalent angles, I can think about just counting how many pi over 6s I have across the entire unit circle. Okay, so let's think about for the next piece. Here's 1 pi over 6. Well, to get to the next one, that would be 2 pi over 6s. Now, of course, 2 pi over 6 simplifies to pi over 3. So this angle is pi over 3. Now I go to my next one, right? This angle here is also 30 degrees, or pi over 6 radians. So now I have 1 pi over 6, 2 pi over 6s. This would be 3 pi over 6. And again, I can simplify this particular one into pi over 2. So this angle has a radian measure of pi over 2. Now let's again remember what that means. That means if you were to walk from here to here, you would walk a distance of pi over 2, whatever the units happen to be. Pi is about 3, so that would be about 1.5, roughly. Okay, but exactly it's pi over 2. Let's keep going. This was 3 pi over 6s, so the next one would be 4 pi over 6s. Okay, so 4 pi over 6, that simplifies to 2 pi over 3. Let's keep going. This one would be 5 pi over 6s. And then I'd have 6 pi over 6s. Now that part should really make sense here. 6 pi over 6, that would just be pi. Again, to go all the way around, it takes 2 pi. So I've gone halfway. That should be pi then. Okay, so it looks like we're on the right track. Okay, so again, this was 6 pi over 6, 7 pi over 6, 8 pi over 6. Again, I'm just looking at the yellow ones. 8 pi over 6 simplifies to 4 pi over 3. This would be 9 pi over 6. 9 pi over 6 simplifies to 3 pi over 2. 10 pi over 6, or 5 pi over 3. So that was 10 pi over 6. 11 pi over 6. And 12 pi over 6. Well, that is 2 pi. Okay, so we've gone all the way around. We just split the circle into fractions, into 12 different pieces. So each of those pieces is going to be worth an angle of pi over 6. This angle, of course, here, forgot that one, is 0. All right, we are going to do the same thing, but now for the orange ones, the ones that are split into 8 pieces. And let's think about what each one is worth. Okay, so again, I'd have 2 pi radians total, split into 8 pieces. Each one of them is going to be worth pi over 4 radians. So let's go ahead and label these now. So again, I start here at 0. That means then to go to the orange angle, I went pi over 4 radians. Okay, I went 1 pi over 4. Now I've gone 2 pi over 4s. Notice that's the same thing as pi over 2. Okay, now I've gone 3 pi over 4s. And now I've gone 4 pi over 4s, or just pi. 5 pi over 4s. 6 pi over 4s, that would be 3 pi over 2. 7 pi over 4s. And 8 pi over 4, that would be 2 pi. Okay, so there we go. We've just labeled our unit circle with all of the corresponding kind of nice radians, the nice angles that we have. Okay, so that's the way that you can fill out your unit circle. Just think about, you have 1 pi over 6, 2 pi over 6, etc. And it might take a little while at first, but as you keep going, you'll be able to do it faster and faster. All right, so now that we have talked about the radians on the circle, another thing that we're interested in, and maybe actually even the most interested in, is the x and y coordinate for those pertaining angles, the nice ones that we've labeled so far. So what we want to do now is we're going to go ahead and figure out what these x and y coordinates are. Let's go ahead and start at the nice angles that we actually already know the value for. So here, for example, this point. Now again, this is a radius of 1, and so I can see that the x coordinate then would be 1, and the y coordinate, well, there really is no y coordinate, so 0. Right, it's not above or below the x-axis, so our y coordinate is 0. And so let's think about some other ones that we already can figure out without doing any sort of other work. Seeing this one right here, the x coordinate is 0, and the y coordinate is 1. If we come back over here, now we're on the negative side as far as the x-axis goes. So this would have an x coordinate of -1 and a y coordinate again of 0. And down here, same x coordinate, but now a negative y coordinate. Okay, so we figured out those 4 points, pretty straightforward. The other ones are a little bit trickier, but one of the great things is once we get this one and this one, we'll be able to get all of the other ones without having to do any more work. Okay, so let's go ahead and take a look at one of these. I'm going to go ahead and do the one for pi over 4 first. So what we're going to do is we're going to think about bringing kind of a line down here, and I'm going to create a triangle. And this is going to be a right triangle. And the reason I want to do that is because I see that this length is the x coordinate, and this length is the y coordinate. So if I can just figure out the lengths of those sides of the triangle, then I will be able to figure out what the x coordinate is here and what the y coordinate is here. Okay, so I'm going to kind of jump over here, and let's go ahead and draw that triangle. Okay, and again, it was a right triangle. And there are some things that I know here. For example, the hypotenuse. I know that the hypotenuse is going to be 1 because this is the unit circle. And I'm going to go ahead and call this x, and I'm going to call this y. Another thing I know is that this angle, the one up to the orange, is pi over 4 radians, Or in this case, we might want to go ahead and talk about degrees. That would be 45 degrees, and so that means that this side would also have to be 45 degrees because there are 180 degrees in a triangle. Now, one great thing here is these angles are the same, and that means that these corresponding sides are also the same. X and Y are equivalent. So what we're going to do, because I have a right triangle, that means that I can use the Pythagorean theorem, and that's exactly what we are going to use. The Pythagorean theorem says I take this side squared plus this side squared, and it should equal the hypotenuse squared. That's 1. Now, one quick thing I'd like to also point out is that this is the equation of the unit circle, because no matter where you go, if you take the x-coordinate and the y-coordinate, square them and add them, you should always get 1, because the hypotenuse or the radius is 1. Okay, now from here, because of the fact that I know that x and y are equivalent, then I could rewrite this so that it's in terms of a single variable instead of in terms of 2 variables, and that's going to allow me to solve. Doesn't matter which one you do, I'm going to go ahead and choose x. So I'm going to replace this y with an x, set that equal to 1, and here I have 2x squared equals 1. We're solving for x, right? That's our goal here. X squared equals 1/2. And then I can square root both sides. I have the square root of the numerator, which is 1, over the square root of the denominator, which would be the square root of 2. Now, this probably doesn't look that familiar. If you've done, oops, sorry, I went off the screen a little bit there. 1 over root 2 probably doesn't look that familiar to you as a coordinate on the unit circle. So there's a few different ways we can think about this. A lot of times we want to what we call rationalize the denominator, multiply by root 2 over root 2, which essentially is 1. This gives me the square root of 2 on top. Root 2 gives me 2 on the bottom. Okay, that's a little bit more traditional to how we label that particular point. Another way you can think about it is 1/2 is the same thing as 2/4, and you can square root, you get square root of 2 over square root of 4, which would be the same thing. Okay, so that tells me then that the x-coordinate here is the square root of 2 over 2, which means that the y-coordinate is also the square root of 2 over 2. So let's go ahead and label that point. So that was this one right here, root 2 over 2, root 2 over 2. Okay, all right, so from here, then let's figure out what the other one is. Okay, so here I have my angle of pi over 6, and I'm going to come all the way out here. We again have a right triangle, and let's go ahead and draw this one. Okay. All right, so again, I'm going to go ahead and choose degrees here. This is pi over 6 radians, or 30 degrees. That would make this angle 60 degrees. And again, this side is the x-coordinate, this side is the y-coordinate. The hypotenuse, or the radius, is 1. Okay, so unfortunately, in this particular case, these two sides are not equivalent to each other. So I can't quite use exactly what I had here. We're going to do just a little trick, okay? And that little trick is to try to turn this into a triangle that has all same angles and all same sides. So if I just think about reflecting this triangle over here, that would create this one, like so. This is still a 90-degree angle. So this is the exact same triangle, just flipped over. And now what I have is then this angle. It was 30, but now I've doubled it. It's 60. This angle was the same as this one, 60 degrees. And now I have an equilateral triangle. So that means that if all the angles are the same, then all the sides are also the same. Okay? So that actually will help me to automatically really find my y-coordinate. I know that these two sides here, this side and this side, are both y. When I add them together, I get 1. Well, y would have to be 1/2 then. Another way of thinking about it is this side length is 2y. I want that side to be 1, so then of course we can just solve for y. Y is 1/2. Okay, so there's the y-coordinate. Now the great thing is that once we have the other side of the triangle, we can figure out what this side is, again based on the Pythagorean theorem. So I have x squared plus y is 1/2, that equals 1, and 1/2 squared is 1/4, and we'll subtract that 1/4 to the other side, giving us 3/4. And one last step, solving for x, we'll square root both sides, which is the same as square rooting the top over square rooting the bottom, and I get √3/2. So there's my y-coordinate, there's my x-coordinate. Okay, again, these are two different pieces here. So this is for a 45-45-90, this is for a 30-60-90. I have these as my sides of the triangle. Okay, so that means then that the x-coordinate here is the square root of 3/2. The y-coordinate is 1/2. And one thing I'd like to point out here is if you look at this point, you kind of think about following it across, well, it does look like the y-coordinate is 1/2, doesn't it? It goes exactly halfway between 0 and 1. So we kind of probably could have seen that one without even doing all the work necessarily. Okay, now like I mentioned, just getting these two triangles now, we can finish the entire rest of the unit circle. Okay, so pi over 3, well this is going to be the exact same triangle as this one. It's just going to be, now this side would be the same as this side, and this side would be the same as this side. So all we need to do is flip those. This has an x-coordinate of 1/2 and a y-coordinate of √3/2. And again, we can kind of see that here. If I think about following this down, it looks like it's halfway between. Okay, now from here, now that I have the first quadrant, it's going to allow me to get all of the rest of them because they're all going to be the same values, just different signs, depending on which quadrant it's in. So if I look here, for example, I can see that the y-coordinate is the same, √3/2. The x-coordinate is the same, but it's negative, -1/2. Here, x-coordinate is negative, √2/2. Y-coordinate is positive. Same thing here, negative x-coordinate, positive y-coordinate. Down here, they're all negative. So I see that the x-coordinate is negative √3/2. This would be -1/2. Negative √2/2, negative √2/2. Again, this is a 45 one, so I'm corresponding to this point here. This one would be the same as this, but switched, -1/2, negative √3/2. And here, same y-coordinate, same x-coordinate, but positive. This one has a positive x-coordinate, but a negative y-coordinate. And this one has a, again, same thing, -1/2. There we have it. Okay, so there's our entire unit circle, all nice and filled out with our radians and with our x and y coordinates. Okay, so this brings us to kind of really the main reason for looking at this, and that is now we want to start talking about sine and cosine, our various trig functions. Okay, so on the unit circle, the x-coordinate is given by, oops, sorry about that, the cosine of the angle, and the y-coordinate is given by the sine of the angle. Okay, that's just something that you'll want to remember, of course. So that means now that if I wanted to know certain values here, I can just think back to my unit circle about what those corresponding coordinates are. Okay, so one other one that we are interested in too is the tangent of the angle. And the tangent of the angle isn't really all that visual on the unit circle necessarily. It's not given by side lengths. It can be written like that, but I'm not going to go into that. Essentially what tangent tells you is the slope of the line. So that's the y-coordinate over the x-coordinate. Or another way to think of that is the sine of the angle over the cosine of the angle. Okay? All right, so let's go ahead, now that we have our unit circle filled out, what I'd like you to do is go ahead and evaluate the following. So go ahead and just pause the video, go through and evaluate all of these Try your best not to look at the unit circle, but you can go ahead and use that as a last resort. Okay, let's go ahead and go over this. So we have the sine of pi over 4. Now I know that with pi over 4, that was like our 45, 45, 90 triangle. And so I know that that corresponds to x and y coordinates of the form the square root of 2 over 2. So the question is then, first, where is pi over 4? So let's go ahead and draw the circle. And we can again think about our counting. So I know that 45 degrees is pi over 4. I really don't have to count in this particular case because it's just 1 pi over 4. So that puts me here. I can see that the sign is a positive number, and it is the square root of 2 over 2. Similarly, if we look at the cosine of pi over 3, the first thing we'll want to do is go ahead and find pi over 3. So I know that with my pi over 6's, I had 1 pi over 6, 2 pi over 6, right? Pi over 3 is the same thing as 2 pi over 6. So 2 pi over 6's puts me right here. Now I want the x coordinate because it's cosine. So I'm going to think about following this down. I know that it's either 1/2 or root 3 over 2 because pi over 3 corresponds to a 30, 60, 90 triangle, which has only these as possible sides. And I can see visually that it is 1/2. It's exactly halfway in between, so 1/2. The sine of 2 pi over 3, think about finding that. Again, 2 pi over 3 would be 4 pi over 6's. So I'd have 1 of them, 2 of them, 3 of them, 4 of them, 4 pi over 6's. And I want the sine. Similar, I know it's going to be root 3 over 2 or 1/2. If I just think about drawing a line across, I can see it's clearly not 1/2. 1/2 is here. So it's larger than that. It's root 3 over 2. And it's positive because my y coordinate is positive there. Cosine of 3 pi over 2. Okay, let's find 3 pi over 2. In this particular case, you could think of this as a pi over 6 or a pi over 4, or if you already know that this is pi over 2, then this would be 1 pi over 2, 2 pi over 2's, 3 pi over 2's. So that puts me right down here. I can see the cosine, the x coordinate is 0. Sine of 7 pi over 6. That one's already written over 6 for me, so that's kind of nice. Let's skip a little bit. I know over here is pi. That would be 6 pi over 6's, so we just want to go one more. There's 7 pi over 6's. And again, it's going to be either 1/2 or root 3 over 2. If I follow across, it looks like it's 1/2. Not only that, but it's a negative because it's down in the third quadrant, which has negative y values. Cosine of 3 pi over 4. Okay, I have 1 pi over 4, 2 pi over 4's, 3 pi over 4's. And I know this one corresponds to the square root of 2's over 2's because it's one of our 45, 45, 90 triangles. So from here, I can just think about what sign it should be. I see it's a negative, so it should be negative root 2 over 2. All right, let's talk about tangent. Tangent of 5 pi over 6 would be the same thing as the sine of it over the cosine. So we really just need to evaluate both of these. So let's think about a unit circle. And 5 pi over 6 is just 1 pi over 6 shy of pi. It'll be right here. Okay, or again, you can do the counting. 1, 2, 3, 4, 5. And I want the sine, which looks like positive 1/2. And I want the cosine, which is negative root 3 over 2. So let's go ahead and just simplify that a little bit. Negative reciprocate 2 over root 3. And my 2's cancel, and I get negative 1 over root 3. Now it's okay to leave the root 3 in the denominator, that's fine. All right, now from here, let's just also think about what that means. Again, tangent tells you what the slope of the line is. So that is if I connect this point with this point, the tangent of the angle is the slope of that line. So it looks about right. It is negative, that's good. And it's not very steep really. It's 1 over root 3, not very steep. All right, let's take a look at the tangent of 7 pi over 4. Now I'm actually going to do this one without any calculation because you'll see why we can do that. Again, I have 1 of them, 2, 3, 4, 5, 6, 7. Or I could have thought about 8 pi over 4. 1 less than that would be 7 pi over 4. Okay, so this one, I can think about this line essentially and what its slope is. Now I know that at this point, this is 7 pi over 4, the x and y coordinate are essentially the same. They have the same value, they just have different signs. So at this point, if I take the rise over the run, well, the rise and the run are the same. It's just we have a negative of that. So I'd have -1 for my slope. Again, it's because the x and y coordinate are the same at that point, just differing in sign. Okay, so this really is just about everything you would need to know to at least evaluate particular trig functions.